Good day, my name is Dr. John Steele, University of New South Wales, Sydney, Australia. This is my second video on sketching in 3 dimensions. In the first video I went through some basics. The key points were use a pencil, try and draw axes that are actually not at right angles on the page so that they actually look like they're proper perpendicular axes. And thirdly, if you're going to draw a surface, draw the surface first and put the axes in afterwards, trying to make sure that you get some sense of proper perspective in that. In this video I'm going to go on to talking about drawing more general surfaces, not completely general surfaces. I'm going to concentrate on the 2 surfaces that you will see most often in your Calculus 3 or multivariable calculus courses: surfaces of revolution and quadric surfaces. So, what is surface of revolution? As the name suggests, it's a surface got by revolving some curve around some line, typically around one of the coordinate axes. Simplest example is probably the sphere, which you can get by rotating a semicircle around an axis. And what's a graph of semicircle? Well, here's an example. Suppose we had the curve z is 1 minus x squared. X, of course, would be between minus 1 and 1. Revolve that around the x-axis, it's going to sweep out a sphere. The sphere x squared plus y squared plus z squared equals 1. What would happen, for example, if you were to do something else? Suppose you were to take the line z equals x and rotate that around, say, the z-axis. Well, you hopefully can picture that. It would sweep out a cone. In fact, sweep out the cone given in 3 dimensions by z is the square root of x squared plus y squared. I think we want x to be positive here, don't we? If we had x free, we'd actually get a double napped cone, right? We get what looks like 2 cones put together. And this is telling us something about how you recognize these things from their equation. If 2 of the variables only turn up as a sum of squares, then that's telling you that you're going to have a surface of revolution, and the other variable is going to be the one forming the axis. So this is x squared plus y squared. X and y only occur as sum of squares, z doesn't. It's a curve got by rotating something around the z-axis. And similarly here. Not so obvious for a sphere, of course, because you could rotate the semicircle around any axis you like. So, in sketching a surface of revolution, the first step is to work out which one of the coordinates is going to give me the axis of rotation. And as I've just said, that's going to be the coordinate that doesn't appear in the sum of squares. So let's assume, for example, for the sake of argument, that that's z in this case. If it's not z, by the way, do draw that axis of rotation vertical and then put the axis in afterwards, making sure you get the handedness correct. So if you've got a surface formed from revolving some curve around the z-axis, the equation of the surface will be something like z is some function of x squared plus y squared. That's a function of one variable, or always x squared plus y squared, like f is a sine of x squared plus y squared. Or it might be given more implicitly as some function of x squared plus y squared, and z, function of 2 variables, is equal to 0. That's a constraint form. So in both these cases, as I said, z is going to be our axis of revolution. So that's the one we're going to draw as vertical. So the next step in drawing is to draw what we call a profile curve, typically an x-profile curve. It could be the y one, doesn't make any difference. You set y to be 0 in these equations, and you draw the curve that you get in the zx plane. So drawing the curve z equals f of x squared, or big F of x squared z equals 0. And once you've got that, we go to the next thing. This is simplest done by an example, so let me try and show you what happens if you draw the simple surface. Z is x squared plus y squared, known as a paraboloid. Again, we've got the right axis here. So the first step is to draw our vertical z-axis. Let me get the colours right. And we're going to draw the surface, the curve z equals x squared, which of course is a parabola. Now I could put in the horizontal axis here, and then draw it, or I could leave it off. Now, I mentioned in the first video that people often draw 3D diagrams where they have this sort of set up for x and y, and then they just draw y coming out like this or going back, whatever. The reason they do it is because basically they're just being lazy. They're doing what I'm doing here, drawing up a surface of revolution, but without fixing up the axes afterwards. It's not the end of the world if you don't do this, fix the axes up, but you might as well. So that's why you would draw this quite lightly, typically. So to get back to our example, z equals x squared is what we want to draw. That's a parabola. Now remember, you could turn the page over to get to draw the parabola with the your hand on the inside. I can't do that with a whiteboard. This will be good enough though. So that's our parabola. Oh, that's not particularly balanced, but it'll do. There'll be occasions, by the way, where you might want to just draw for x. You might just have a curve for x positive, and you might have to put the sort of the reflection in the z-axis in just to complete the circle. Because what we're going to get here, we're going to take this parabola and rotate it around the z-axis. That's what we're trying to sketch up here. And if there isn't a curve there, you're going to have to add it in. Not in this case, it's not a problem. But to make it look like it's rotation, mock up sort of a circle, which of course would involve doing some sort of ellipse here, and ellipse around there, which will go behind the z-axis, so it should be broken, and that's going to be our basic shape. This is the z-axis pointing here. Notice the z-axis will be partially hidden, right, from here downwards. It's inside, so let's dash that axis, and let's put the x-axis at a better angle, so we have a slightly neater looking picture. Not quite necessary to do this bit, but as I said, not any harder. I mean, if you'd only drawn that, if you'd missed the axis off or just drawn it lightly, this is a very easy thing to do. X-axis, y-axis, z-axis, and that's my paraboloid of revolution. Not perfect, but good enough for what we're going to do. There might be in cases where you're going to have to do more fiddling around with dashing bits of the axes, but that's usually pretty obvious. Quadric surfaces. A quadric surface is a surface whose equation is typically an implicit equation, is a polynomial of degree 2. A general polynomial degree 2. So it involves terms like x squared, y squared, x, y, z, and constants. We've already met a couple of examples. The sphere is a quadric surface. It's x squared plus y squared plus z squared minus 1 equals 0. The paraboloid is a quadric surface. It's x squared plus y squared minus z equals 0. But something like this, let's make one up on the spot. Z equals it's x squared plus y squared minus z equals 1. That is not a quadric surface because it's got a zx squared, which is a cubic sort of term. Right? So that's not going to be a quadric surface. Now, many of the quadric surfaces you meet in practice are actually surfaces of revolution, and so it could be drawn like that. So something like x squared plus y squared minus z squared is 1. That's a surface known as a hyperboloid of one sheet. It's got, by rotating the curve, the hyperbola, x squared minus z squared equals 1 around the z-axis. So that's how you would draw it. Right? So the profile curve, let's put it here, shall we, is a hyperbola, and then you've got to draw a hyperbola on the other side. And then the usual rotation sort of thing. Oh, that should be solid, shouldn't it? This is the one that should be dashed. And then you've got a curve around there. And then you'd put your axes in, and you get your hyperbola of one sheet. And you can use this sort of shape once you know these quadric surfaces. I'm not going to go into how you work out what quadric surface is what. That's an entire chapter of a course in linear algebra typically. You could get something similar just by, if you've got a similar shaped curve, something that's not, say, x squared, but say a 2x squared and a minus 7 z squared. It's the same rough shape, but you just stretch and squeeze the axes as is necessary to get yourself something that looks the right sort of shape. So what do we do for more general surfaces? Maybe it's a quadric surface you don't recognize. Well, the standard trick here is to take the equation, set one of the coordinates to be 0, and that's going to give you a curve in one of the coordinate planes. essentially find the intersection of the surface with the various coordinate planes and then try and stitch them together as best as you can. As a simple example, let's look at this surface. This is actually a quadric surface. 2x squared plus 3y squared plus say 7z squared is 1. Put z equals 0, what's the intersection with the xy plane? Well, hopefully you recognise that as an ellipse. And similarly though, intersection with the xz plane, an ellipse, intersection with the yz plane, an ellipse. So this is going to have elliptic intersections, so you're going to take 3 orthogonal ellipses and put them together, and that's going to be a surface known as an ellipsoid. It looks vaguely like a sort of squashed sphere. And since the z here is, well, where is it going to intersect the z-axis? Well, when x and y are both 0, so z is 1 upon root 7, so it's actually more squashed in the z-axis than in the other direction. But this is one of those cases where you might quite regularly want to draw the axes in non-standard positions. Doesn't make much difference if you do here. So this is the sort of shape we're going to get. It's not particularly brilliantly drawn, but no, it's a bit too pointy at that end for an accurate ellipsoid, but that will be good enough. You don't have to get anything perfect. Then you can put the axes in. You need to do that if that's what you want. Now, in some cases for more complicated surfaces, you might actually just have to generalize that. You might have to look at the intersections of the surface with other planes. For example, you might look at what happens when you set z equal to 1 or z equals 2, and there you'll get what are known as level curves. And again, you can try drawing these level curves and try and stitching them together. It's a bit of mental gymnastics, but that's what's going to be involved whenever you try drawing surfaces in 3 dimensions, a little bit of mental gymnastics. Now, I hope that some of what I've said will be useful to you, even if it's only the simple point of drawing the surface first and putting the axes in afterwards. But I want to finish off by doing an example, which is one of the hardest examples typically, students find it hard anyway, that we get you to draw. The hyperbolic paraboloid. Z is x squared minus y squared, or z equals xy will be another example of it. This is a surface that's really very hard to draw if you try and do the axes first and then the surface afterwards. Much easier to do it the way around I've suggested. Hyperbolic because, well, we've got hyperbolas here. Parabola, well, we've got z is x squared sorts of curves and z equals minus y squared. Those are parabolas. We're going to have parabolas on the surface put together in a sort of a hyperbolic way. But once you recognize this surface, and you could get that by drawing some of those intersections with the planes like I suggested earlier, then you should recognize it as some sort of saddle-shaped surface. That's another name for it, a saddle surface. So that's what you draw. You draw the saddle surface and then put the axes in. And so this one will look like this, roughly. So saddle-shaped surface, that's going to be roughly a parabolic, and it'll come down here, around the end there, and then it'll become hidden. Then we'll have this here, roughly parabolic there, down to about there, I suppose. And then this edge is hidden. Come down here. Okay, so there we've got, trying to get the picture here of parabolas going that way and this way, but if you were to slice this with z is some constant, you'd get a hyperbola. So that's why the hyperbolic paraboloid is called what it is. And what are the axes here? Well, z-axis would be here, so at this point. Whoops. And the x-axis points along this way roughly, hidden here. Merges about there and back this way. Merge there. And the y-axis. Well, that's a good enough angle for the y-axis, I think. And this way. And then it'll be partly hidden underneath. Oh, no, oh, sorry, it will in fact be all the way on top. Yeah, I've drawn it. That is the hyperbolic paraboloid. You want to neaten it up, could sort out that intersection there, of course, because that axis is in front of the surface. So as I say, I hope this has helped and at least encourage you to try drawing these surfaces with some idea of the perspective, without worrying too much about how accurate it is. Actually isn't usually an important factor here. It's getting the right picture so that you can go on to do the next bit that you've got to do, typically finding areas and surface integrals and things like that.